Welcome to Late Space. I'm grateful you've chosen to spend this evening with us. Perhaps your mind is racing from the day's events, or maybe you simply prefer to drift into sleep while contemplating the vast mysteries that surround us. Whatever brought you here, you've made the right choice. Tonight requires nothing from you except to be present. Allow your muscles to soften, your breath to deepen, and feel yourself becoming weightless, as though the bed beneath you has dissolved into starlight. Tonight's voyage takes us through our galactic home, the Milky Way, an ancient wheel of light that has been spinning through the void for billions upon billions of years. Within its spiraling arms lie mysteries that challenge our understanding, wandering suns, forces we cannot see, and remnants so old they existed before our galaxy took its current form. We'll drift peacefully from its glowing arms inward to its concealed heart, from titanic mergers to suns that remember when the universe was young. What you encounter tonight might intrigue you, or perhaps it will simply provide a peaceful backdrop as consciousness fades. Before we embark, if you find these tranquil cosmic explorations valuable for unwinding after long days, please consider supporting the channel with a like and subscription. It allows more people to discover this peaceful corner of the internet, one restful night at a time. Now, let us begin our journey. The Milky Way is built from galactic cannibalism. Our galaxy appears permanent and unchanging in the night sky, but this stability is an illusion. The Milky Way has consumed dozens of smaller galaxies throughout its history, drawing them inward through gravity's patient pull, dismantling their structures and redistributing their stars into long streams that wind through space. The Sagittarius Dwarf Elliptical Galaxy is currently being torn to pieces, its stars slowly absorbed into our galaxy's mass. Meanwhile, the Andromeda Galaxy moves toward us through the darkness. In approximately 4 to 5 billion years, these two massive spirals will begin their merger, a collision so vast it will unfold over billions of years. Individual stars will rarely collide due to the immense distances between them, but the galactic structures will transform completely, eventually settling into a new elliptical form. Galaxies, despite their grandeur, are not permanent. They grow, merge, and transform. Ancient stars predate the galaxy itself. Some stars currently orbiting within the Milky Way are older than the galaxy's disk structure. These ancient halo stars, depleted of heavy elements and travelling on steeply inclined paths, likely formed in primitive dwarf galaxies that merged with our own during the early universe. Their spectral signatures reveal they contain almost no elements heavier than helium, indicating birth in the universe's first billion years. They drift slowly through the halo, high above the main disk like ancient witnesses from an era before organized galactic structures existed. Their faint light carries information about a cosmos that was simpler, more turbulent, and still in the process of organizing itself into the patterns we observe today. Our solar system races through the galaxy. The Sun and its family of planets orbit the galactic center at approximately 828,000 kilometers per hour. That velocity translates to roughly 230 kilometers traveled every second. Despite this tremendous speed, completing one full orbit requires about 225 to 250 million years. Astronomers call this span a galactic year. Since the solar system's formation roughly 4.6 billion years ago, we have completed only about 20 circuits around the Milky Way. When dinosaurs first appeared on Earth, our solar system occupied a completely different position within the galaxy. The stellar neighborhood we observe today has changed dramatically over geological time, and it will continue transforming. While we sleep, the Earth rotates, the Moon traces, its orbit and our entire solar system sweeps through a galaxy that never stops moving. The galaxy continues accumulating mass. Though the Milky Way is approximately 13.6 billion years old, its growth has not ceased. The galaxy continues gathering material from its surroundings, gas from the cosmic web, stars from captured satellite galaxies, and dark matter that feeds its massive halo. This growth doesn't resemble biological development, but rather the gradual deepening of a gravitational well over cosmic time. Some accretion happens quietly as diffuse clouds settle into the disk. Other times, growth is violent, as when satellite galaxies are shredded and their stars scattered across the sky in tidal streams. The Milky Way your ancestors saw was smaller. The one future generations may observe could be larger still, assembled from countless smaller systems. The number of spiral arms remains uncertain. It seems we should know something so fundamental about our home galaxy. How many major spiral arms extend from its centre? Yet from our position embedded deep within the disk, determining the exact number proves remarkably difficult. Obscuring dust clouds block our view of distant regions. Stars at various distances blend together visually. For many years, astronomers believed 4 major spiral arms defined the structure. More recent observations using infrared and radio telescopes suggest perhaps only 2 major arms exist, with several minor branches and spurs. Some arms appear to fragment into smaller pieces, others exhibit unexpected twisting patterns. The Milky Way may not resemble the neat pinwheel spiral often depicted in illustrations, but instead forms a more complex layered swirl shaped by forces we're still working to understand fully. Hypervelocity stars escape the galaxy. Most stars drift peacefully through the Milky Way, following orderly orbits around the galactic centre. However, a small population of stars has been accelerated to such extreme velocities that they will escape the galaxy entirely. These hypervelocity stars, moving faster than 500 kilometers per second, often originate from binary star systems that wandered too close to Sagittarius A star, the supermassive black hole at our galaxy's core. In these encounters, one star may be captured or consumed while its companion is catapulted outward at tremendous speed. These rogue stars travel alone through the halo and beyond, like luminous projectiles with no hope of return. They serve as reminders that even in a structure bound by gravity, violent ejections occasionally hurl stars into the intergalactic void. Collision with Andromeda is inevitable. Visible to the naked eye as a faint smudge in autumn skies, the Andromeda Galaxy lies approximately 2.5 million light-years distant. Despite this vast separation, Andromeda and the Milky Way are approaching each other at about 110 kilometers per second. In 4 to 5 billion years, they will collide. The encounter won't be destructive in the way we typically imagine collisions. Stars are separated by such vast distances that direct impacts between individual stars will be extraordinarily rare. Instead, the gravitational interaction will distort both galaxies, stretching them into elongated shapes with extended tidal tails curling into space. The central supermassive black holes will eventually spiral together and merge. After several billion years of gravitational chaos, the 2 galaxies will settle into a single, larger elliptical galaxy. It will be an elegant slow-motion transformation, the future of our cosmic neighbourhood written in the movements of stars. Some stars move backward through the galaxy. The vast majority of stars in the Milky Way orbit the galactic centre in the same general direction, following the galaxy's overall rotation. But some stars, particularly in the outer halo, move in retrograde motion, orbiting opposite to this dominant flow. These backwards moving stars almost certainly originated elsewhere, likely forming in dwarf galaxies that were subsequently absorbed by the Milky Way. Their reversed motion serves as a permanent record of their foreign origin, a kinematic signature of ancient mergers. The galaxy carries these memories in motion, stories of past collisions and captures, preserved not in light or chemistry, but in the persistent, patient orbits of stars swimming against the stream. Dozens of dwarf galaxies have been consumed. The Milky Way has not grown in isolation. It has actively consumed smaller galaxies over billions of years. Faint dwarf companions caught by our galaxy's gravitational field have been gradually dismantled their stars now distributed throughout our halo, disk, and in stellar streams. Astronomers have identified evidence of numerous such mergers by analysing the motion, position, and chemical composition of stars. One particularly significant event, the Gaia-Enceladus merger occurring approximately 10 billion years ago, added substantial mass to the Milky Way and may have fundamentally altered the young galaxy's structure. Our galaxy is not a pristine original creation, but rather a composite structure assembled from numerous smaller systems that no longer exist as independent entities. Stellar chemistry reveals. Origins. Every star carries a distinct chemical signature, a unique pattern of elemental abundances imprinted during its formation. By analysing these signatures through spectroscopy, astronomers can trace individual stars' histories. Stars rich in iron, calcium, and other heavy elements likely formed in dense, metal-enriched regions within the galactic disk. Others contain almost pure hydrogen and helium, indicating formation during the universe's first billion years when few heavy elements existed. These compositional differences allow scientists to group stars into populations, identify remnants of ancient mergers, and reconstruct the hidden history of the Milky Way's assembly. Chemical analysis becomes a form of temporal archaeology, permitting us to read a star's past like ancient writing encoded in light. Stellar streams trace destroyed galaxies. Across the sky, thin ribbons of stars stretch in graceful arcs and curves, nearly invisible individually but unmistakable when mapped precisely with modern telescopes. These stellar streams represent the scattered remains of smaller galaxies that approached too close to the Milky Way and were pulled apart by tidal forces. As these doomed satellites orbit, their stars are stretched across space by differential gravitational forces, forming delicate trails that mark their former trajectories. Some streams wrap around the galaxy like ghostly rings, others plunge toward the central regions. These streams provide evidence of past encounters, quiet mergers that constructed the Milky Way over cosmic time. Like growth rings in a tree, they carry records of the galaxy's accumulation history in every thread of starlight. The galactic disk is warped. Our galaxy doesn't lie perfectly flat like an idealized spiral. The disk bends upward on one side and downward on the other, creating a subtle wave across the galactic plane. This warp remained undetected until radio telescopes mapped the distribution of neutral hydrogen gas, extending far beyond the visible starlight. Astronomers believe the distortion may result from gravitational interactions with satellite galaxies tugging on the Milky Way's edges, or from asymmetric distributions of dark matter below the disk. Like ripples propagating through a vast spinning sheet, the warp reveals that galaxies are never truly static. They bend, flex, and transform in response to unseen forces acting over millions of years. From sufficient distance, the Milky Way might appear to undulate slowly as it rotates. We see only a tiny fraction of stars. Under perfectly dark skies, far from artificial light pollution, the human eye can detect perhaps 5,000 to 6,000 individual stars. To our perception, this seems like an overwhelming multitude, but it represents barely 0.00003% of the Milky Way's total stellar population. The galaxy contains an estimated 100 to 400 billion stars. Most remain hidden from our view, obscured by thick dust clouds or simply too faint and distant for human vision to resolve. The pale band of the Milky Way visible on moonless nights shows only the nearest, brightest concentration of the whole. We exist surrounded by a colossal river of starlight, yet the vast majority remains forever invisible to our unaided eyes, too immense to comprehend from our position within it. Stars orbit at different speeds. Unlike planets in our solar system, which follow well-defined Keplerian orbits with velocity decreasing with distance, stars in the Milky Way move with more complex patterns. Stars in inner regions orbit more rapidly, while those in outer areas move more slowly relative to the center. However, the difference is less dramatic than Newton's laws would predict for visible matter alone. This velocity pattern is why spiral arms form and persist. They're not rigid structures rotating as a unit, but rather density waves, like cosmic traffic jams where stars and gas temporarily bunch together. As material passes through these waves, compression triggers new star formation, illuminating the arms with bright blue-white young stars. Our Sun drifts in and out of these patterns over time. The galaxy is not a clockwork mechanism but a flowing current, and we drift within it. Dark matter binds the galaxy together. By all logical calculations based on visible matter, the Milky Way should not exist in its current form. Based on what we can observe directly, stars are gas, dust. The outer regions of the galaxy rotate too rapidly. They should be flung outward into space like water off a spinning wheel. Yet they remain bound to the galaxy. The explanation lies in dark matter, a mysterious substance that neither emits nor absorbs electromagnetic radiation of any wavelength. But it exerts gravitational force, and there is so much of it that it outweighs all visible matter in the galaxy by a factor of roughly 10 to 1. We don't know what dark matter is composed of, but without it the Milky Way would disintegrate. It forms an invisible scaffolding that maintains galactic structure. A supermassive black hole anchors the centre. At the precise centre of the Milky Way lurks an enormous black hole designated Sagittarius A star. This gravitational singularity contains more than 4 million times the Sun's mass, yet occupies a region of space smaller than Mercury's orbit. We cannot observe it directly through any form of electromagnetic radiation, but astronomers have tracked nearby stars whipping around it at tremendous velocities, tracing invisible ellipses through empty space. Occasionally gas and dust fall inward, flaring with X-rays as material spirals toward the event horizon. Currently, Sagittarius A star appears relatively quiet, but evidence suggests that in the distant past it may have blazed like a quasar, illuminating the entire galaxy from within. It remains the silent gravitational anchor of the Milky Way's heart, conducting stars in their slow, relentless orbital dance. The central bulge has an unusual shape. When astronomers carefully mapped the galaxy's central region, they discovered an unexpected geometry. The central bulge is not a smooth, spherical concentration of stars, but exhibits a three-dimensional peanut or X-shaped structure. Viewed from certain angles, it swells in the middle and narrows at the ends, resembling a twisted hourglass constructed from billions of stars. This peculiar morphology likely formed from the galaxy's central bar, a dense elongated structure that rotates slowly, buckling vertically and puffing upward over billions of years. These inner structures are sculpted by complex gravitational dynamics, accumulated stellar orbits, and billions of years of evolution. We inhabit a spiral galaxy, but its core reveals unexpected complexity, neither flat nor simple, but intricate and dynamically active. Spiral arms mark star-forming regions. The Milky Way's spiral arms are not merely concentrations of existing stars, but active sites of stellar birth. Giant molecular clouds composed of hydrogen, dust, and trace molecules drift through the galaxy. When these clouds encounter the density waves defining spiral arms, they're compressed, triggering gravitational collapse and igniting new generations of stars. These regions are called stellar nurseries, chaotic and luminous environments filled with newborn stars, protoplanetary disks, and glowing nebulae. Ultraviolet radiation from hot young stars illuminates surrounding clouds, painting the arms with brilliant blues and whites. These bursts of stellar creation trace out the spiral pattern, defining the galaxy's visible structure with light from stars that will burn for billions of years. Every star, including our Sun, originated in one of these cloudy nurseries long ago. A vast halo surrounds everything beyond. The familiar spiral disk extends something far less obvious, a roughly spherical halo that envelops the entire galaxy. This halo contains ancient stars, globular clusters, stellar streams from disrupted satellites, and enormous quantities of dark matter. Though nearly invisible, the halo may contain the majority of the Milky Way's total mass. Its stars are distributed sparsely across vast volumes, orbiting on long, slow trajectories that rarely intersect the disk. The halo also preserves remnants of ancient galactic mergers, shells and streams of stars torn from smaller galaxies and abandoned like archaeological fossils. It represents the galaxy's outer memory, dim and quiet, but still in motion, still shaping the Milky Way's continuing evolution. Over 150 globular clusters orbit the galaxy. Globular clusters rank among the oldest structures in the Milky Way. These compact spheres contain hundreds of thousands to millions of stars gravitationally. Bound in dense configurations, they orbit the galactic center within the halo like moths circling a distant flame. Many clusters are extraordinarily stable, with ages exceeding 12 billion years, and numerous members contain stars that predate the Milky Way's current structure. Their stars are metal poor, indicating formation before the universe had synthesized many heavy elements through stellar nucleosynthesis. They serve as temporal capsules, preserving information about how the galaxy formed, what it absorbed, and conditions prevailing in the early cosmos. These quiet golden spheres drift patiently above and below the galactic plane, glowing softly in the darkness. Star formation has slowed. Over time, billions of years ago, the Milky Way exhibited far more vigorous star formation, with dense collapsing clouds producing new stars at high rates. In more recent epochs, the pace has declined significantly. Sufficient gas remains available, but much is dispersed, heated, or exists in forms that resist collapse. The galaxy continues forming stars, but at a more sedate pace. Astronomers estimate that star formation peaked approximately 10 billion years ago and has been steadily decreasing since. This doesn't indicate imminent death, only that we live during a quieter chapter, a mature spiral glowing gently in middle age, still birthing stars but no longer rushing. Some stars formed before the disk existed. The disk, the broad flattened spiral structure we associate with the Milky Way, formed gradually over billions of years. However, some stars currently in our galaxy are older than the disk itself. These ancient stars reside primarily in the halo, or the thick disk, and they formed when the galaxy was still assembling, existing as a loose cloud of gas, stars and dark matter slowly collapsing under its own gravity. By studying their chemistry, age, and motion, astronomers can peer into the era before organized structure existed, before spiral patterns emerged. These stars are the galaxy's elders, silent observers of its birth and the long gradual process that shaped what we now call home. A galactic year spans hundreds of millions of Earth years. As our solar system orbits the galactic center, it completes one full revolution every 225 to 250 million years. This duration defines a galactic year, a vast cycle of motion that dwarfs all human timescales. During a single galactic year, continents drift across Earth's surface, mountain ranges rise and erode, species evolve and go extinct, and entire geological eras unfold. The solar system is currently about halfway through one such orbit. The last time we occupied this position in the galaxy, the supercontinent Pangaea was beginning to fragment and dinosaurs had not yet evolved. A galactic year represents the slow pulse of cosmic time. The Sun has completed fewer than 25 orbits. Throughout its entire 4.6 billion year existence, the Sun has circled the Milky Way approximately 20 times. This seems surprisingly few considering the Sun's tremendous orbital velocity of nearly 830,000 kilometers per hour. But the galaxy is so immense and the Sun's orbital path so long that each circuit requires hundreds of millions of years. We often conceive of stars as ancient and unchanging fixtures, but our solar system remains relatively young on galactic timescales, a newcomer in a metropolis populated by older, more travelled stars. We participate in the galaxy's grand motion but remain early in its long winding narrative. Galactic rotation defies simple physics. According to classical Newtonian mechanics, stars farther from the galactic centre should orbit significantly more slowly, just as outer planets in our solar system move more leisurely than inner ones. However, in the Milky Way, stars in outer regions orbit almost as quickly as those near the centre, producing a nearly flat rotation curve. This behaviour contradicts predictions based solely on visible matter. The explanation, astronomers believe, involves dark matter, an invisible, unknown form of mass surrounding the galaxy in an extended halo. Without dark matter, observed rotation would tear the galaxy apart. With it, the mathematics work out. The Milky Way rotates somewhat like a solid wheel, not because we fully understand the physics, but because something unseen maintains coherence. Giant molecular clouds span vast distances. Scattered throughout the Milky Way exist vast, dark clouds of cold molecular gas, the raw ingredients for star formation. These molecular clouds, composed primarily of molecular hydrogen, along with traces of dust and other molecules, can span hundreds of light years. Within their frigid, dense interiors, gravity gradually accumulates material, forming clumps that collapse to create new stars and planetary systems. Some clouds are so large and cold they absorb visible light completely, appearing as black voids against the starry background. They represent the galaxy's nurseries, quiet hidden places where the future begins in silence, concealed within curtains of shadow and molecular gas. Supernovae shape the galactic environment. When massive stars exhaust their nuclear fuel, they explode as supernovae, cataclysmic events so powerful they can briefly outshine entire galaxies. These explosions do more than end stellar lives, they actively create. Shock waves from supernovae propagate through the interstellar medium, compressing nearby clouds and triggering new waves of star formation. They enrich surrounding space with heavy elements like iron, gold, and uranium forged in the dying star's core and during the explosion itself. Supernovae function like storms within the galactic ecosystem, stirring, fertilizing, and reshaping their surroundings. They represent the galaxy's moments of chaos, destructive and radiant yet essential for ongoing evolution. Dust obscures. Star-forming regions. The Milky Way contains vast quantities of light we cannot see. Interstellar dust, composed of microscopic grains of carbon, silicates, and ice, weaves through the galaxy in clouds and filaments. In visible wavelengths, it obscures large regions of space, blocking stars and entire nebulae from view. Yet behind this veil, star formation continues unabated. Infrared and radio telescopes can peer through the dust, revealing brilliant nurseries filled with nascent suns. What appears as darkness often conceals beginnings. The dust, though it hides, participates in the process, absorbing energy, facilitating gas cooling, and protecting delicate stages of stellar birth. Apparent emptiness frequently marks the birthplace of something luminous. Starless gas clouds drift dormant. Not every molecular cloud produces stars. Throughout the Milky Way, astronomers have discovered massive cold clouds that appear destined for collapse yet remain dark and inactive. Some are too diffuse to collapse. Others may be stabilized by magnetic fields or internal turbulence. These starless clouds float through the galaxy like dormant potentials, rich in molecular hydrogen but untouched by fusion. They may eventually ignite under the right conditions, or they may drift until disrupted by external forces, their gas recycled into other regions. In these clouds, the galaxy seems to hold its breath, waiting perhaps for the proper trigger to spark something new. The galaxy recycles matter. Continuously, stars are not eternal. They form, burn, and die, returning their material to the galaxy in the process. Supernovae distribute heavy elements across interstellar space. Red giants shed outer layers into planetary nebulae. White dwarfs slowly cool over trillions of years. This enriched material joins the interstellar medium, where it cools, condenses, and eventually forms new generations of stars, planets, and potentially life. Every atom in your body has cycled through this process multiple times. Born in a star, scattered into space, incorporated into new structures. The Milky Way is not a static stage, but a vast engine of renewal, breathing in harmony with its stars, continuously creating, destroying, and beginning again. Metal-poor stars preserve primordial chemistry. In astronomical terminology, metals refer to all elements heavier than helium. The earliest stars in the universe contained almost none of these metals because they formed before previous stellar generations could forge and disperse them through supernovae. Today, astronomers actively search for metal-poor stars in the Milky Way's halo. These faint ancient stars preserve chemical conditions from a bygone era. By analysing their composition through spectroscopy, we glimpse the primordial past, the period shortly after the Big Bang, before galaxies had matured and before heavy elements became common. They are fossils constructed from light itself. Many stars have migrated from their birthplaces. A star's formation site doesn't necessarily determine its final location. Over time, many stars drift away from their natal clouds, displaced by gravitational interactions, orbital resonances, or the slow influence of spiral density waves. Some stars are ejected at high velocities, flung across the disk or into the halo through multi-body encounters or supernovae and binary systems. Others migrate gradually, shifting their orbits inward or outward as they spiral through the galaxy over hundreds of millions of years. Even our Sun is not where it began. Tracing stellar paths reveals a Milky Way far from static, a galaxy alive with movement, exchange, and continuous redistribution. Home for a star may be temporary. The galaxy may have a habitable zone. Just as Earth orbits within a Goldilocks zone around the Sun, neither too hot nor too cold for liquid water and life, the Milky Way may possess its own galactic habitable zone. This region likely lies between the hazardous inner core, filled with intense radiation and gravitational chaos, and the sparse metal-poor outer edges where planetary systems may be rare. Somewhere between these extremes extends a broad band where conditions are stable, stellar density moderate, and elements necessary for rocky planets and life are abundant. Earth resides within this zone, one quiet orbit in a vast swirl where life might not be alone in establishing a foothold. Spiral arms are dynamic patterns, the Milky Way's spiral arms might appear to be permanent features, grand sweeping structures carved into the galactic disk, but they are not composed of fixed stellar populations. Instead, they represent patterns, density waves that propagate slowly through the disk, compressing gas and triggering star formation as they pass. Stars drift into these arms, shine brightly during their residence, then drift out again over tens of millions of years. The spiral structure itself moves at a different speed than individual stars, like a traffic jam propagating through a highway independent of specific vehicles. From outside, it appears orderly and structured. From within, it's a pattern of shifting motion maintained by gravity and time, never still, always flowing. The galaxy radiates across many wavelengths beyond visible light. The galaxy glows with more enigmatic forms of energy. Cosmic rays, high-energy particles born in supernovae and beyond the galaxy, stream through space, passing through your body every second. X-rays and gamma rays emanate from stellar remnants and black holes. Radio waves drift from gas clouds, pulsars, and the cold emission of neutral hydrogen. These invisible radiations reveal what optical light cannot: violence, magnetism, and ancient fires still flickering within the galaxy's structure. When you gaze at the night sky, you're observing only a narrow slice of the Milky Way's true spectrum. Beneath visible stars, the galaxy hums softly across many frequencies, a hidden symphony in the darkness. The Milky Way contains stellar fossils from different eras. Throughout the galaxy exist distinct stellar populations that tell the story of different formation epochs. Population 1 stars, like our Sun, are relatively young, metal-rich, and found primarily in the disk. Population 2 stars are older, metal-poor, and concentrated in the halo and bulge. Some astronomers even discuss population 3 stars, theoretical first-generation stars composed of only hydrogen and helium that have never been directly observed but must have existed to create the first heavy elements. Each population represents a different chapter in the galaxy's history, written in starlight and chemistry. By studying these populations, we read the Milky Way's autobiography page by page, epoch by epoch. The galactic centre is obscured by dust lanes. If you look towards Sagittarius on a clear summer night from the northern hemisphere, you'll notice dark patches interrupting the bright glow of the Milky Way. These are not empty voids, but dense clouds of dust blocking the light from billions of stars beyond. The galactic centre lies behind these obscuring lanes, completely hidden from optical view. Only infrared, radio, and X-ray observations can penetrate this barrier, revealing the chaotic, crowded environment at the galaxy's heart. We live in a galaxy whose core we cannot see with our eyes, a reminder that our home harbours secrets behind veils of cosmic dust. Star clusters reveal the galaxy's formation. History, open clusters, and globular clusters serve as archaeological artifacts, preserving information about the conditions prevailing when they formed. Open clusters, found in the disk, are relatively young and metal-rich, often still embedded in or near their natal gas clouds. Globular clusters, orbiting in the halo, are ancient and metal-poor, some of the oldest objects in the galaxy. By dating these clusters and analysing their chemistry, astronomers reconstruct the timeline of galactic evolution. Each cluster is like a snapshot frozen in time, showing us what the galaxy was like at different stages of its long life. The Sun's galactic orbit is not perfectly circular. While we often describe the Sun as orbiting the galactic centre in a circle, the reality is more complex. The orbit is slightly elliptical, and the Sun oscillates vertically through the galactic plane as it travels. Additionally, the Sun's path is influenced by the gravitational effects of spiral arms, molecular clouds, and other massive structures it encounters. Over millions of years, these perturbations create small variations in the orbit. The Sun's journey through the galaxy is not a perfect geometric curve, but a meandering path through a gravitationally complex environment, influenced by everything it passes. Stellar winds shape the interstellar medium. Stars don't just shine passively. They actively blow material into space through stellar winds. Young hot stars can produce incredibly powerful winds that shape surrounding nebulae and clear out cavities in molecular clouds. Old, dying stars shed their outer layers more gently, but still contribute significant mass to the interstellar medium. These winds carry energy and momentum, stirring the gas between stars and helping to regulate the temperature and density of the interstellar environment. Over millions of years, stellar winds from countless stars sculpt the galaxy's internal structure, creating a constantly evolving landscape of gas and dust. The galaxy has experienced multiple growth phases. The Milky Way's assembly was not a single, smooth process, but occurred in distinct phases. Early on, the proto-galaxy collapsed from a diffuse cloud, forming the first generation of stars. Later, the disk began to form as gas settled into a rotating plane. Throughout this time, smaller galaxies merged with the growing Milky Way, adding mass and stirring the structure. Some of these mergers were major events that fundamentally altered the galaxy's shape and stellar populations. Others were minor additions that simply added streams of stars to the halo. Understanding these growth phases helps astronomers piece together the chaotic early history of our galactic home. The thick disk may result from ancient mergers. The thick disk, that puffier layer of older stars above and below the thin disk, poses an interesting puzzle. Its origins are debated, but many astronomers believe it formed during ancient mergers with smaller galaxies. When a satellite galaxy crashes into a larger disk, the collision can heat the disk, puffing it up and creating a thicker structure. The chemistry and kinematics of thick disk stars support this merger scenario. They show signatures of mixing between different stellar populations. The thick disk, then, is not just a structural feature but a scar, evidence of violent encounters billions of years ago that helped shape the Milky Way we see today. Molecular hydrogen is difficult to detect directly. The most abundant molecule in the galaxy is molecular hydrogen, the raw material for star formation, yet it's remarkably difficult to observe directly. Molecular hydrogen doesn't emit much radiation at the cold temperatures of molecular clouds. Instead, astronomers often trace it using carbon monoxide, which emits radio waves more readily and is thought to be well mixed with hydrogen. This indirect detection method works well but introduces uncertainties. The true distribution of molecular hydrogen throughout the galaxy, therefore, must be inferred rather than directly measured, adding a layer of mystery to our understanding of star formation's raw ingredients. The galaxy's stellar mass is approximately 60 billion suns. While the total mass of the Milky Way, including dark matter, may exceed 1 trillion solar masses, the stellar mass, the actual mass in stars, is much smaller. Current estimates place it around 60 billion times the Sun's mass, though this number carries significant uncertainty. This means that for every kilogram of material locked in stars, there are many more kilograms in gas, dust, and especially dark matter. Stars, the most visible components of the galaxy, represent only a tiny fraction of its total mass. We see the bright lights but miss the vast dark ocean in which they float. Supernova remnants glow for thousands of years. When a massive star explodes, the expanding shell of debris continues glowing for millennia. These supernova remnants, visible across the electromagnetic spectrum, appear as delicate filaments and shells of hot gas. The Crab Nebula, one of the most famous remnants, has been expanding for nearly 1,000 years since Chinese astronomers witnessed the supernova in 1054 CE. Other remnants are much older, faded and dispersed but still detectable in radio and X-ray wavelengths. These structures reveal the violence of stellar death and the mechanisms by which stars enrich their surroundings with heavy elements. They are cosmic monuments to destruction and creation intertwined. The galactic habitable zone may shift over time. The concept of a galactic habitable zone, regions where conditions favour the development of life, is not static. As the galaxy evolves, this zone may shift. In the early galaxy, supernovae were more frequent everywhere, potentially sterilising many regions with intense radiation. As star formation has slowed, the galaxy has become generally more hospitable. Additionally, the Sun's orbit carries us through different galactic neighbourhoods over time. We may have passed through spiral arms with higher supernova rates or drifted through quieter regions. Life on Earth has experienced the galaxy's changing nature throughout its existence, subject to influences that vary over tens of millions of years. Brown dwarfs are failed stars throughout the galaxy. Not every collapsing gas cloud becomes a star. Objects with less than about 8% of the Sun's mass lack sufficient core pressure to sustain hydrogen fusion. These brown dwarfs exist in a twilight zone between planets and stars, glowing dimly from residual heat but never igniting true stellar fusion. The Milky Way may contain billions of these failed stars, difficult to detect because they're so faint. They represent a hidden population, a reminder that the galaxy contains far more objects than just luminous stars and planets. Brown dwarfs drift through space, slowly cooling over billions of years, invisible to most surveys yet gravitationally present. The galaxy's rotation period varies with distance. Different parts of the Milky Way rotate at different speeds, creating what astronomers call differential rotation. Near the centre, the rotation period is very short, just a few million years. In the solar neighbourhood, it's about 225 million years. Far out in the halo, orbital periods can exceed 1 billion years. This differential rotation creates shear forces that stretch and distort structures in the disk. It's why spiral arms can't be permanent features composed of the same stars. Differential rotation would wind them up too tightly. Instead, the arms must be transient patterns, density waves propagating through a disk that rotates at different speeds at different radii. Planetary nebulae illuminate the interstellar medium. When stars like the Sun reach the end of their lives, they shed their outer layers gently, creating expanding shells of gas called planetary nebulae. Despite the name, they have nothing to do with planets. Early observers thought they looked planet-like through small telescopes. These beautiful structures, illuminated by ultraviolet light from the hot stellar core at their centre, glow in spectacular colours. They last only tens of thousands of years before dispersing into the interstellar medium, but during that brief time they return material enriched with carbon, nitrogen, and other elements to the galaxy. Planetary nebulae are the final artistic expression of medium-mass stars, their last contribution to the galactic ecosystem. The galaxy's angular momentum is conserved. As the proto-galaxy collapsed billions of years ago, it retained the angular momentum from the initial cloud's rotation. This rotation prevented a complete spherical collapse, and instead led to the formation of a rotating disk. The conservation of angular momentum is why galaxies form disks rather than spheres. Material can collapse along the rotation axis, but not perpendicular to it without losing energy through collisions. This fundamental physical principle shaped not just the Milky Way, but spiral galaxies throughout the universe. Our flat, rotating galactic home is a direct consequence of physics governing rotating, collapsing clouds of gas. The Milky Way's X-ray emission reveals high-energy processes. When observed in X-ray wavelengths, the Milky Way reveals a completely different character. X-ray binaries, where compact objects like neutron stars or black holes accrete matter from companion stars, appear as bright point sources. Supernova remnants glow with thermal X-rays from shock-heated gas. The galactic centre blazes with emission from hot plasma, and possibly from near the supermassive black hole. Diffuse X-ray emission traces hot gas in the halo. This X-ray view shows us the most energetic processes in the galaxy, events involving extreme temperatures, rapid accretion, and powerful magnetic fields that remain hidden in visible light. Molecular clouds are structured and filamentary. Modern observations have revealed that molecular clouds are not uniform blobs, but possess intricate internal structure. They contain filaments, cores, and hierarchical nested structures on multiple scales. These filaments, dense threads of gas snaking through the clouds, appear to be where stars preferentially form. The filamentary structure may arise from turbulence, magnetic fields, and gravity working together to shape the cloud's interior. Understanding this structure is crucial for understanding star formation. Stars don't form randomly throughout a cloud, but in specific locations where the density and conditions are just right, often along these filamentary highways of molecular gas. The galaxy emits infrared radiation from dust. When observed in infrared wavelengths, the Milky Way glows warmly with radiation from dust grains. These grains, heated by starlight, re-emit the absorbed energy as infrared radiation. This infrared glow allows astronomers to map the distribution of dust throughout the galaxy and peer into regions obscured in visible light. Infrared observations reveal hidden star formation in molecular clouds, trace the spiral arms through dusty regions, and even allow us to see through to the galactic centre. The infrared Milky Way is a different galaxy from the optical one, showing us structure and activity that visible light cannot reveal. Stellar streams are discovered through careful surveys. Stellar streams, those faint ribbons of stars from tidally disrupted satellites, are incredibly difficult to detect. They're composed of individual stars spread across huge volumes of space, appearing no different from foreground and background stars when viewed individually. Only through careful statistical analysis of large surveys can astronomers identify these streams. By plotting stars' positions, velocities and chemistry, patterns emerge. Lines of stars moving together, sharing similar compositions, tracing out ghostly arcs across the sky. These discoveries are triumphs of big data astronomy, finding order in what appears to be chaos, revealing the galaxy's hidden history one stream at a time. The Milky Way's central black hole is relatively quiet. Compared to supermassive black holes in other galaxies, Sagittarius, a star is remarkably quiet. It accretes very little material currently, producing only faint emissions across the spectrum. This quiescence is somewhat puzzling given the dense stellar environment and abundant gas near the galactic centre. Why doesn't more material fall into the black hole? The answer may involve magnetic fields, stellar winds, and the specific dynamics of the central region that prevent efficient inflow. However, evidence suggests Sagittarius A star was more active in the past. The Fermi bubbles and other features hint at outbursts within the last few million years, brief episodes of intense activity punctuating long periods of dormancy. The galaxy's future is shaped by dark energy. While gravity has assembled the Milky Way over billions of years, a mysterious force called dark energy dominates the universe on larger scales. Dark energy causes the expansion of space to accelerate, driving distant galaxies ever farther apart. However, gravitationally bound structures like the local group are not affected by this expansion. They remain held together by their mutual gravity. This means that while the universe expands and distant galaxy clusters recede, the Milky Way, Andromeda, and their satellite galaxies will remain gravitationally bound, eventually merging. Dark energy determines which galaxies we can ever interact with, and which will recede beyond our cosmic horizon forever. Old stars in the halo reveal chemical evolution. The most metal-poor stars in the galactic halo provide crucial insights into chemical evolution. Each generation of stars produces heavy elements through fusion and supernovae, enriching the interstellar medium for the next generation. By studying stars with different metallicities, astronomers can trace this enrichment history. The oldest, most metal-poor stars formed from nearly pristine gas, containing only elements from the Big Bang. Progressively younger stars show higher metal content, documenting how the galaxy chemically evolved over billions of years. This chemical archaeology reveals not just the history of individual stars, but the entire galaxy's maturation. The Milky Way will eventually become isolated. In the far future, as dark energy continues driving cosmic expansion, galaxy clusters beyond our local group will recede beyond the cosmic horizon, their light redshifted to invisibility. Eventually, only the local group galaxies will remain visible, merged into a single giant elliptical galaxy. Astronomers in that distant epoch, trillions of years from now, will see a very different universe, a single island galaxy surrounded by darkness, with no evidence of the vast cosmic web we observe today. The universe's expansion, accelerated by dark energy, means our descendants will inherit an increasingly empty sky, isolated in a merged galaxy with only ancient light from the distant past reaching them. Stellar archaeology uncovers the galaxy's past. By studying old stars in detail, astronomers practice what they call stellar archaeology, using living stars to reconstruct the galaxy's history. Each star's chemical composition reflects the gas from which it formed, which in turn reflects all previous stellar generations. Stars with unusual abundance patterns may have formed in specific environments, or from gas enriched by particular types of supernovae. Stars with retrograde orbits likely came from accreted satellites. Through careful analysis of thousands of stars' spectra, positions, and motions, astronomers reconstruct events billions of years in the past, uncovering mergers, starbursts, and transformations that shaped the Milky Way into what we observe today. The galaxy's gas content is gradually depleting. Star formation requires gas, primarily hydrogen, to form new stars. Over billions of years, the Milky Way has been converting its gas reservoir into stars. While fresh gas continues flowing in from the intergalactic medium and some is recycled from dying stars, the net effect is a gradual depletion of the galaxy's gas supply. Billions of years from now, when most of the available gas has been exhausted and inflows cease, star formation will slow to a trickle and eventually stop. The galaxy will fade as old stars die, and no new ones form to replace them. We live in an era when the Milky Way still has abundant gas and active star formation, but this will not last forever. Tidal forces from satellites affect the disk. The gravitational pull from satellite galaxies like the Magellanic Clouds doesn't just affect those smaller galaxies, it also influences the Milky Way itself. The tidal forces from these satellites can excite waves in the outer disk, contributing to the warp and potentially triggering star formation as they pass. Some astronomers believe that encounters with satellites may have been responsible for creating some of the spiral structure we observe. These interactions are subtle but persistent, slowly reshaping the disk over millions of years. The Milky Way is not an isolated, unchanging structure, but one constantly responding to gravitational influences from its cosmic neighbours. The galactic year defines long-term cycles. Because a full orbit around the galaxy takes approximately 225 million years, many processes in the solar system operate on timescales measured in fractions of galactic years. The Sun's vertical oscillation through the galactic plane, for instance, occurs about 4 times per galactic year. The Sun's passage through spiral arms might occur several times per orbit. Some researchers have even speculated about correlations between mass extinction events on Earth and the Sun's galactic motion, though these remain controversial. Thinking in terms of galactic years provides a useful perspective for understanding long-term patterns and cycles that would otherwise seem random on shorter timescales. White dwarfs will outlive almost everything. When medium-mass stars like the Sun exhaust their nuclear fuel, they become white dwarfs, dense stellar remnants about the size of Earth, but containing roughly the Sun's mass. These objects no longer generate energy through fusion, but simply radiate away their residual heat over trillions of years. White dwarfs cool incredibly slowly, meaning many of the white dwarfs formed early in the galaxy's history are still glowing today. Eventually, over timescales far longer than the current age of the universe, they will cool completely, becoming black dwarfs. Cold, dark remnants that no longer emit visible light. These objects will be among the last things shining in an aged, dying galaxy. The Milky Way's visible light comes mostly from main sequence stars. When we observe the Milky Way in visible light, most of the luminosity comes from main sequence stars, stars like the Sun that are fusing hydrogen into helium in their cores. Though giant stars and supergiants are far more luminous individually, they're also far rarer. Main sequence stars dominate simply through their sheer numbers. However, different wavelengths tell different stories. In infrared, cool giant stars contribute more. In ultraviolet, hot young stars dominate. In X-rays, we see compact remnants. Each wavelength reveals a different stellar population, showing us the galaxy through different eyes, emphasizing different aspects of its complex stellar population. Cosmic voids surround rich regions. The Milky Way resides within a larger structure called the local sheet, a flattened distribution of galaxies that includes the local group. This sheet lies between 2 large cosmic voids, vast regions of space containing few galaxies. These voids are not truly empty, but are significantly underdense compared to regions like the local sheet. The structure of the universe on these scales resembles a cosmic web. Filaments, sheets, and clusters of galaxies surrounding vast empty voids. Understanding our position in this web helps explain the Milky Way's environment and the distribution of nearby galaxies we observe. The galaxy's magnetic field may have multiple reversals. Like Earth's magnetic field, the galactic magnetic field may undergo reversals where its polarity flips. Evidence for this comes from studying the magnetic properties of interstellar gas at different distances from the galactic plane. These reversals would occur over millions of years and might be driven by dynamo processes in the disk or by external influences. Such reversals would affect cosmic ray propagation, the shapes of supernova remnants, and perhaps even the interstellar environment that solar systems like ours pass through. The galactic magnetic field is not static, but dynamic, potentially flipping and changing over the galaxy's long history. Young stars trace the galaxy's recent star formation. The younger stars in the Milky Way, particularly hot massive O and B stars, have very short lifespans, just a few million years. Because they die so quickly, these stars must still be near their birth sites. By mapping the distribution of young stars, astronomers can identify active star-forming regions and trace the current sites of stellar birth. These young stars illuminate nebulae with their intense ultraviolet radiation, creating the beautiful glowing clouds we see in images of the galaxy. They also produce powerful stellar winds that shape their surroundings. Despite their brief lives, these stellar giants have outsized effects on the galactic environment. The galactic corona extends far beyond the disk. Surrounding the Milky Way at great distances is a galactic corona, an extended region of hot, diffuse gas with temperatures reaching millions of degrees. This corona is difficult to observe but has been detected through absorption lines in the spectra of distant quasars whose light passes through it. The corona may contain a significant fraction of the galaxy's normal matter, rivaling the mass of gas in the disk. Understanding this corona is crucial for accounting for all the normal matter that should exist in the galaxy based on cosmic abundances. It may also play a role in regulating star formation by providing a reservoir of gas that can cool and fall into the disk. Resonances shape galactic structure. Orbital resonances occur when two objects' orbital periods form simple ratios. In the Milky Way, resonances between stellar orbits and the rotation of spiral arms or the central bar create special locations where gravitational forces reinforce certain orbital properties. These resonances can trap stars in specific orbits, create gaps in the disk, or enhance star formation. The corrotation resonance, where stellar orbits match the pattern speed of spiral arms, is particularly important. The Lindblad resonances, where the orbital and pattern frequencies form simple ratios, define the inner and outer edges of spiral arms. These resonances create order within the apparent chaos of galactic dynamics. The Sun's elemental abundances are not universal. For many years, the Sun was considered a standard reference for elemental abundances, a typical star with typical composition. However, detailed surveys of other stars have revealed that the Sun is actually somewhat unusual. Its metallicity is slightly higher than the average for stars of its age in the solar neighbourhood. This means the molecular cloud from which the Sun formed may have been enriched by a nearby supernova just before collapse. Understanding these variations is important for studying exoplanets because a star's composition affects the types of planets that form around it. The Sun and Earth are products of a specific local environment, not necessarily representative of the galaxy as a whole. Massive stars are cosmic, chemical factories. The heaviest stars, those with masses exceeding 10 or 20 solar masses, live fast and die young in spectacular supernova explosions. During their brief lives, they fuse elements all the way up to iron through various nuclear burning stages. When they explode, they not only disperse these elements but also produce even heavier elements through rapid neutron capture during the explosion itself. These massive stars are the primary source of elements like oxygen, magnesium, silicon, and iron that make up rocky planets and living organisms. Without the short, violent lives of massive stars, the galaxy would lack the chemical diversity necessary for planets and life. The galaxy's star formation rate has declined. Measurements of stellar ages reveal that the Milky Way formed stars much more vigorously in the past. The star formation rate peaked approximately 10 billion years ago and has been declining ever since. Currently, the galaxy converts about 1 to 3 solar masses of gas into stars each year, a modest rate compared to its peak. This decline reflects the gradual depletion of gas, the increasing difficulty of accumulating dense molecular clouds in an enriched interstellar medium, and perhaps changes in the rate of gas inflow from outside. This gradual quieting is a normal part of galactic evolution, characteristic of mature spiral galaxies in the present-day universe. Galactic archaeology combines multiple approaches. Understanding the Milky Way's history requires combining many different techniques. Stellar ages from radioactive dating or astroseismology provide temporal information. Chemical abundances reveal the enrichment history. Kinematics show how stars move and identify distinct populations. Spatial distribution shows structure. Together, these approaches allow astronomers to reconstruct the galaxy's formation and evolution. It's like assembling a vast jigsaw puzzle, where each star provides a small piece of information. Only by studying thousands or millions of stars can the full picture emerge. Modern surveys collecting data on billions of stars are revolutionizing this field, turning galactic archaeology from a handful of case studies into a statistical science. The Milky Way's interstellar extinction varies. As light from distant stars passes through interstellar dust, it is both dimmed and reddened, a phenomenon called extinction. The amount of extinction varies greatly depending on the direction you observe. Toward the galactic plane, where dust is concentrated, extinction is severe, blocking optical light completely in some directions. Perpendicular to the plane, where less dust intervenes, extinction is minimal. This variable extinction must be carefully accounted for when studying the galaxy. A star may appear faint not because it's distant, but because substantial dust lies between us. Astronomers must correct for extinction to accurately determine stellar properties and distances. Globular clusters may have formed in different environments. The Milky Way's globular clusters are not all the same age or composition. Some appear to have formed in the protogalaxy itself, while others likely formed in dwarf galaxies that were later accreted. This diversity reveals itself in their chemistry, ages, and orbits. Some globular clusters have unusual stellar populations, including multiple generations of stars with different helium abundances, a puzzle still not fully understood. These differences suggest that globular clusters formed through various mechanisms in different environments throughout the early universe. They are not a homogeneous population, but a diverse collection of ancient stellar systems with complex origins. The galaxy's disk has been heated over time. The velocity dispersion of stars in the disk, how much their orbits deviate from perfectly circular, increases with stellar age. Older stars have more random elliptical orbits, while younger stars move on calmer, more circular paths. This suggests that the disk has been gradually heated over time through gravitational interactions with spiral arms, molecular clouds, and passing satellites. Each encounter adds a small kick to stellar orbits, slowly increasing the disk's thickness and velocity dispersion. This heating is a natural consequence of the galaxy's dynamic environment, where stars constantly experience weak, gravitational perturbations that accumulate over billions of years. The Milky Way's mass-to-light ratio reveals dark matter. When astronomers calculate the total mass of the Milky Way from its rotation curve and kinematics, then compare this to the total luminosity from stars, they find a large discrepancy. The mass-to-light ratio is much higher than can be explained by stars, gas, and dust alone. This difference is one of the key pieces of evidence for dark matter. Visible matter simply cannot account for the gravitational effects we observe. Something else, dark matter, must be present in large quantities. This invisible component dominates the galaxy's mass budget. and fundamentally shapes its structure and evolution, even though we cannot directly detect it. The galactic fountain cycle takes millions of years. Gas ejected from the disk by supernovae and stellar winds doesn't escape the galaxy entirely. Instead, it rises into the halo, cools over millions of years, and eventually falls back onto the disk due to gravity. This galactic fountain cycle redistributes material vertically, mixing gas that has been processed through stars with less processed gas in the outer disk. The cycle helps explain the presence of hot gas in the halo and may influence the rate and location of star formation in the disk. It's a slow breath, the galaxy inhaling and exhaling over timescales incomprehensibly long compared to human experience but crucial for galactic evolution. The Milky Way's formation involved chaotic accretion. Rather than forming smoothly and gradually, evidence suggests the Milky Way's early history was chaotic. Small proto-galaxies and dark matter halos merged in a random fashion, each collision adding mass and stirring the structure. The exact sequence and timing of these mergers determined the final properties of the galaxy we see today. Different merger histories would have produced different galaxies. Understanding this chaotic assembly process helps explain why every galaxy is unique and why even small details of the merger history can have lasting effects on galactic structure billions of years later. Some stars have unusually high velocities. Even among stars bound to the galaxy, some have peculiarly high velocities relative to the local standard of rest. These high-velocity stars may be old halo stars on plunging orbits that bring them temporarily through the disk, or they may be stars given extra kicks by encounters with massive objects. A few may even be interloping stars from other galaxies passing through. These stellar speeders stand out in surveys and often receive special attention because their unusual kinematics may reveal interesting dynamical processes or trace populations with unique origins. Every unusual star is a potential clue to understanding the galaxy's complexity. The galaxy's future merger will create new structures. When the Milky Way and Andromeda merge billions of years from now, the collision will create entirely new structures. Tidal tails stretching hundreds of thousands of light-years will form, composed of stars ripped from both galaxies. New bursts of star formation will likely occur where gas clouds collide and compress. The supermassive black holes at each galaxy's center will eventually merge, creating a single, even more massive black hole and possibly releasing tremendous energy as gravitational waves. The result will be a large elliptical galaxy, sometimes nicknamed Milkomeda, with properties distinct from either progenitor. It will be a new beginning, forged from the collision of two ancient spirals. Stellar flybys can disrupt planetary systems. In the densest regions of the galaxy, stars occasionally pass close enough to one another that their gravitational influence can affect planetary systems. A close stellar encounter could perturb orbits in a system's outer regions, potentially ejecting planets into interstellar space or sending them into highly elliptical orbits. These encounters are rare in the solar neighborhood, but more common in denser environments like star clusters, some of the rogue planets drifting through. The galaxy may have been ejected this way. These flybys remind us that gravitational interactions occur on all scales, from galaxies down to planetary systems. The galaxy's chemical gradient shows inside-out growth. The abundance of heavy elements in stars varies with position in the galaxy. Stars near the galactic center are generally more metal-rich than those in the outer disk. This metallicity gradient suggests the galaxy grew from the inside out, with the central regions forming stars first and enriching quickly, while outer regions formed stars later from less enriched gas. Gas flows and stellar migration complicate this simple picture, but the overall gradient remains. This pattern is common in spiral galaxies and provides important constraints on models of how galaxies assemble and evolve over cosmic time. Neutron stars are among the densest objects. When massive stars collapse in supernovae, their cores may compact into neutron stars, objects so dense that atomic nuclei touch, forming matter in exotic states found nowhere else in the universe. A neutron star contains more mass than the Sun compressed into a sphere just 20 kilometers across. A teaspoon of neutron star material would weigh billions of tons on Earth. These extreme objects dot the galaxy, most invisible except when they're pulsars or accreting matter in binary systems. They represent the ultimate compression of matter this side of a black hole, laboratories for physics under conditions we can never replicate on Earth. The galaxy's history is written in stellar orbits. Because gravity remembers, the orbits of stars carry information about the gravitational potential they've experienced throughout their lives. Stars from accreted satellites maintain signatures of their disrupted galaxy's orbits. Stars kicked by close encounters with massive objects bear the imprints of those encounters. By carefully analysing the three-dimensional motions of millions of stars, astronomers can reconstruct past events, ancient mergers, the passage of massive molecular clouds, the effects of spiral arms. Orbits are a form of memory, preserving the galaxy's gravitational history in the persistent motion of stars that have travelled through it. Giant gamma-ray bubbles extend from the core. Stretching tens of thousands of light-years above and below the galactic centre are two enormous, ghostly lobes of high-energy radiation. The Fermi bubbles, discovered in 2010, glow in gamma rays, extending like twin balloons from the Milky Way's heart. Scientists remain uncertain about their origin. They may represent remnants of a long-ago outburst from the central supermassive black hole, or marks of intense starburst activity that once flared through the core. Either explanation suggests the galaxy has a violent past we cannot fully reconstruct. These enormous structures drift silently over the galaxy, invisible to human eyes, reminders that the Milky Way's history contains events we're only beginning to understand. Echoes of violence wrapped in high-energy light far above the familiar stars. We live between major spiral arms. Our solar system doesn't reside within one of the Milky Way's grand spiral arms. Instead, we occupy a minor structure called the Orion Spur or Local Arm, a relatively quiet branch of stars nestled between the larger Sagittarius and Perseus arms. It's neither especially dense nor especially active, but that may explain why we're here. In this calm region between galactic highways, massive supernovae occur less frequently. Radiation bursts are rarer. This quiet location may have provided life on Earth the stability it required to emerge and evolve over billions of years. From outside perspectives, the galaxy appears dramatic and radiant. But in this peaceful spur, we found sufficient tranquility for biological complexity to unfold. The galaxy has a bar-shaped centre. When astronomers observe the galactic core using infrared wavelengths, which penetrate obscuring dust, they see not a circular concentration, but an elongated bar of stars crossing the middle, a luminous bridge. This bar rotates slowly, and its gravitational influence shapes the inner spiral arms. Bars are common in spiral galaxies, forming when stars in the disk begin accumulating along a central axis. Over time, the bar becomes a stable structure, stirring gas, triggering star formation, and funneling material toward the central black hole. It's not merely a shape, but a dynamic engine, actively sculpting the galaxy's heart from within through gravitational torques and resonances. The Milky Way belongs to the local group. The Milky Way doesn't exist in isolation, but belongs to a collection of more than 50 galaxies known as the local group, a small gravitationally bound cluster drifting through space together. The two dominant members are the Milky Way and Andromeda, each with its own retinue of satellite galaxies. Scattered around them are smaller dwarfs, faint ellipticals and ultra-diffuse galaxies. The local group spans roughly 10 million light-years and is bound together not merely by proximity, but by mutual gravitational attraction. We are part of a family, widely dispersed but still linked by invisible threads of shared motion and gravitational influence. Local group galaxies are gravitationally bound. Despite vast separations, galaxies in the local group are not drifting apart due to cosmic expansion. Many are actually moving slowly toward one another, their paths curved by mutual gravitational attraction. Some of the smallest galaxies orbit the Milky Way like moons, looping and falling, gradually dissolving into stellar streams. Others drift more independently but remain gravitationally bound, caught in a web of shared motion. Over billions of years, this group may condense further as galaxies merge, fade, or are absorbed. It's not a static arrangement, but a gradual gravitational gathering of cosmic islands, a family drawn closer by time, inertia, and gravity's patient reach. The galactic disk has two components. The Milky Way's disk appears flat from great distances, but closer examination reveals layering. The thin disk is where we reside, a dense plain filled with young, stars, open clusters, and star-forming gas. Above and below stretches the thick disk, older, more vertically extended and more diffuse. Stars in the thick disk tend to be older with lower metallicities. They follow more tilted and elliptical orbits, suggesting formation under different conditions or disturbance by early galactic collisions. The galaxy's disk is not uniform but textured and layered, shaped by time like sediment deposited on an ocean floor over geological ages. A magnetic field threads through the galaxy. Though invisible to optical observation, the Milky Way possesses a vast magnetic field stretching across the disk, extending into the halo and weaving through the interstellar medium. This field is weak by terrestrial standard, but over galactic distances profoundly influences how cosmic rays propagate, how gas clouds collapse, and how matter flows through space. It aligns with spiral arms, forms arcs above the plane, and twists into loops defying simple explanation. Studying it requires radio telescopes and polarization measurements, but its presence is unmistakable. The Milky Way doesn't merely glow with electromagnetic radiation, it breathes with magnetism, a subtle field running through its structure. The interstellar medium contains complex structures. Between stars lies far more than emptiness. The interstellar medium, a tenuous blend of gas, dust, and plasma, permeates the Milky Way like an invisible fog. To unaided vision, it remains. Mostly invisible, but radio and infrared telescopes reveal stunning complexity. It forms filaments, bubbles, shock waves, and cold, dense clouds where stars form. Supernovae carve vast cavities within it. Stellar winds sculpt it into shapes extending across light years. The space between stars is not a void, but a shifting network of matter and energy, the subtle fabric from which galaxies evolve and from which, ultimately, life emerges. Cosmic rays constantly permeate space. Every second, high-energy particles, mostly protons and atomic nuclei, stream through your body at nearly the speed of light. These cosmic rays originate from exploding stars, particle acceleration near black holes, and other violent events. They are omnipresent, travelling close to light speed, bending through magnetic fields, occasionally colliding with atmospheric atoms to create showers of secondary particles. Most pass unnoticed, but they carry information from across the galaxy, evidence of ancient supernovae, traces of particle acceleration, messages from stellar violence. Even as you rest, the galaxy whispers in particles, invisible messengers travelling in silence. The galaxy exhibits asymmetries. Though many diagrams depict it as a neat, symmetric spiral, the Milky Way is not perfectly balanced. One side of the disk appears thicker than the other. Some spiral arms are brighter, longer or more curved than their counterparts. The warp in the outer disk is lopsided. Even stellar counts between hemispheres show slight imbalances. These asymmetries may result from gravitational encounters with satellites, past mergers, or dark matter distribution. They remind us that galaxies, like living organisms, carry traces of their histories in their shapes. Scars from collisions, wrinkles from time, quirks from uneven growth that provide character and individuality. One of the oldest known stars orbits in the halo high. Above the galactic plane drifting through the halo, astronomers have discovered stars that may be nearly as old as the universe itself. Some contain almost no heavy elements, signatures of formation soon after the Big Bang, before multiple generations of supernovae enriched the cosmos with metals. These stars likely formed over 13 billion years ago, long before the Milky Way's disk existed. They burn quietly now with soft red glows, low in mass but immense in historical significance. They are not merely stars but time capsules, living relics from the universe's earliest dawn, witnesses to cosmic history we can barely imagine. The inner galaxy rotates faster than outer regions. In the Milky Way's inner regions, stars orbit the galactic center far more rapidly than those in outer areas. Near the core, gravitational pull intensifies due to concentrated mass from billions of stars, molecular gas, and the supermassive black hole. This causes stars to sweep through tighter, faster orbits, completing revolutions in just a few million years. Far from the center, where our Sun resides, stars orbit more slowly, requiring hundreds of millions of years per circuit. This differential rotation creates twisting shear, stretches spiral arms, and prevents the disk from rotating as a solid body. The galaxy moves like an enormous wheel whose rim lags behind its hub. Density waves create spiral arms. The Milky Way's spiral arms are not fixed chains of stars but patterns formed by density waves propagating through the galactic disk. As gas and dust pass through these waves, compression triggers gravitational collapse and star formation, illuminating the arms with bright young stars. These stars eventually drift out of the density wave while new ones form, creating a self-sustaining pattern. Like ripples in water or traffic congestion on a highway, the arms are dynamic phenomena, constantly in motion yet appearing stable. From great distances they seem permanent. From within, they represent a dance of matter and gravity, shaped by physical processes operating over millions of years. Stars form from collapsing molecular gas. In the dark recesses of the Milky Way, star formation begins in profound silence. Massive clouds of molecular hydrogen, sometimes spanning hundreds of light years, drift through space at temperatures just a few degrees above, absolute zero. Within these clouds, gravity slowly gains dominance. Small regions grow denser and begin collapsing under their own weight. As gas falls inward, it heats, spins, and flattens, forming a protostar at the center. Over hundreds of thousands to millions of years, pressure and temperature increase until nuclear fusion ignites and a new star blazes to life. From the coldest shadows emerge the brightest lights, spun gently into existence by gravity's patient force. Star clusters. Gradually disperse, many stars form not in isolation but in groups, tight clusters born from the same collapsing molecular cloud. These clusters, bound by mutual gravity, drift together for millions or billions of years. But over time they begin dispersing. Tidal forces from the Milky Way's gravitational field, close encounters with other stars, and internal dynamics gradually pull clusters apart. Stars peel away one by one until the cluster fades into the general stellar population, our Sun likely formed in such a cluster billions of years ago. Its siblings are now scattered, dimmed by distance, or lost in the multitude of stars indistinguishable from unrelated neighbours. Hypermetal-poor stars are extremely rare. Among the rarest objects in the Milky Way are hypermetal-poor stars with atmospheres containing almost no elements heavier than helium. Some contain less than 1/10,000th the iron found in the Sun. These stars are believed to be among the first generation born after the very first supernova, carrying only faint traces of enrichment from a universe still forming itself chemically. They are extraordinarily old, extraordinarily pure, and scattered in the halo like distant beacons from cosmic dawn. Each represents a relic, a gravitationally bound signature from an era we can barely access, glowing softly across billions of years. Planetary systems are common. Throughout the galaxy, planets are not rare cosmic oddities, but natural consequences of star formation. As a new star ignites at the centre of a collapsing cloud, a rotating disk of leftover gas and dust surrounds it. Within this circumstellar disk, particles collide, stick together, gather mass, and grow into worlds. Throughout the Milky Way, planetary systems are commonplace. Some contain gas giants and frozen moons. Others feature compact systems with rocky planets orbiting close to dim stars. Some may resemble our solar system, while others defy expectations completely. The galaxy is not merely full of stars, but populated with systems, countless solar families, each with unique configurations, orbits, and potential. Earth orbits. Near the corrotation radius. In the Milky Way, spiral arms rotate at different speeds than individual stars, functioning as moving patterns rather than solid structures. But at a special distance from the centre called the corrotation radius, the average orbital speed of stars matches the rotation speed of the spiral pattern itself. The Sun orbits close to this special zone. This approximate synchronization may help us avoid frequent crossings of spiral arms, regions with higher stellar density, more supernovae, and greater gravitational disturbances. We may inhabit a more stable neighbourhood of the galaxy, protected not by barriers but by orbital resonance, a fortunate accident of our galactic position. The Sun oscillates through the galactic plane. As it orbits the Milky Way, the Sun doesn't maintain a perfectly flat trajectory. Instead, it follows a gentle wave, drifting above and below the galactic plane like a boat bobbing in slow motion, rising and falling over approximately 70 million years per cycle. This vertical oscillation results from gravitational attraction by the galaxy's mass distribution, pulling and releasing the solar system as it moves. Some researchers have speculated whether this motion might influence extinction cycles on Earth, though evidence remains inconclusive. Still, it reminds us that even on its steady path around the galactic centre, the Sun doesn't glide smoothly, but sways gently through three-dimensional space. Dark matter remains. Mysterious. Dark matter constitutes the majority of the Milky Way's mass, yet it has never been directly detected. It neither emits nor absorbs electromagnetic radiation. It passes through ordinary matter as though it weren't there, but its gravitational effects are undeniable. It holds the galaxy together, explains unexpected stellar rotation speeds, and shapes large-scale cosmic structure formation. Without it, the Milky Way would disintegrate. Astronomers detect dark matter not by observation but by watching how it influences visible matter through gravity. It is the galaxy's hidden infrastructure, invisible and silent, yet one of the greatest mysteries in modern science. Decades of searches have yet to identify its nature. Most mass resides outside the visible disk. Most of the Milky Way's visible stars concentrate within the luminous disk, but the majority of total mass resides elsewhere. The galaxy is enveloped by an enormous dark matter halo extending far beyond the farthest stars. This halo dramatically outweighs the disk, holding the galaxy together through gravitational attraction. It's populated sparsely with ancient stars and globular clusters, but its dominant component is unseen. When we envision the Milky Way, we picture spiral arms and starry planes. But that's merely the glowing surface. The mass that defines the galaxy, its gravity, motion, and reach, is mostly hidden, enveloping everything like an invisible shroud. The galactic core may once have blazed as a quasar today. The Milky Way's heart appears relatively quiet, but evidence suggests it was once far more active. The presence of enormous gamma-ray structures like the Fermi bubbles and traces of high-energy emissions reflected in surrounding gas clouds indicate that Sagittarius A star, the central supermassive black hole, may have flared as a quasar within the last few million years. Quasars rank among the universe's brightest objects, outshining entire galaxies as matter spirals into supermassive black holes at tremendous rates. If the Milky Way once burned this way, it would have appeared dramatically different, a spiral wrapped around a blinding heart of radiation. That era has passed, but echoes persist. Galactic structure changes over billions of years. Galaxies may appear timeless in photographs, but they continuously evolve. Spiral arms shift position. Central bars form, strengthen, or weaken. Gas flows inward and outward. Stars are born, age, and die, altering the stellar population. Even the Milky Way's disk shape, warped, rippling, and lopsided, is slowly changing. Encounters with dwarf galaxies and dark matter substructures can bend or twist the disk. Over billions of years, the galaxy's silhouette has transformed like a drifting cloud. The Milky Way of the distant past differs from today's, and future incarnations will differ still. Its beauty lies not in permanence, but in continuous, gradual transformation. Gravitational waves ripple through the galaxy. Throughout the universe, massive objects collide. Black holes spiral together, neutron stars merge, entire galaxies coalesce. These violent events generate gravitational waves, ripples in space-time itself propagating outward at light speed. Though faint by the time they reach us, some waves pass through the Milky Way, distorting space by infinitesimal amounts as they travel. They're incredibly difficult to detect, but observatories like LIGO and Virgo have successfully captured several events. New experiments aim to detect the background hum of gravitational waves filling the cosmos. Even now, as you rest, space-time itself is shifting subtly, not enough to feel, but enough to reveal that somewhere distant, the universe is transforming. Some stars follow, highly elliptical orbits. Not all stars move in roughly circular paths around the galactic centre. Some follow elongated ellipses, their trajectories looping high above and far below the disk, tilted at steep angles from the main plane. These stars likely originate from different sources, remnants of dwarf galaxies absorbed by the Milky Way, or survivors of ancient gravitational upheavals. Their orbits provide clues, three-dimensional maps of the galaxy's chaotic history and invisible mass distribution. By tracing their motion, astronomers reconstruct the unseen architecture of the Milky Way's gravitational field and accumulated history. These stars drift like messengers from disrupted systems, tilted and stretched but still gravitationally bound to the whole. Neutrinos stream through us from galactic sources. Every second, trillions of neutrinos pass through your body, originating from the Sun, supernovae, and cosmic ray collisions in space. The Milky Way bathes in them constantly, yet they are so nearly massless and unreactive that they slip through almost everything without leaving traces. Special observatories buried deep underground or beneath ice attempt to catch, just a few through rare collisions that produce flashes of light. Neutrinos carry information from inaccessible places, stellar cores, collapsing giants, and the galaxy's unseen energetic processes. They are whispers of cosmic fire, nearly invisible messengers from the galaxy's most violent events. Interstellar space is turbulent. Between stars, space is neither smooth nor static. The interstellar medium, composed of thin gas and dust clouds, is stirred by shock waves, magnetic fields, and stellar motion. Temperature variations span orders of magnitude. Material flows collide, mix, and fragment. Clouds stretch, fold, and tumble chaotically. On large scales, this creates a form of turbulence resembling a slow-motion ocean swirling through the disk. Star formation, cosmic ray propagation, and galactic evolution are all profoundly affected by this restless sea. What appears from great distances as calm starlight is, upon closer examination, a dynamic rippling fabric shaped by invisible winds and ancient energies. Rogue planets. may drift through the halo planets are not always bound to stars. Some form normally but are subsequently ejected from their systems through gravitational interactions. Others may form independently without ever having a parent star. These are rogue planets, worlds adrift in the galaxy, cold, dark, and alone. Though difficult to detect, statistical studies suggest billions may exist in the Milky Way, some even in the outer halo where stars are scarce. Without starlight or external warmth, they float unseen, heated only by residual internal heat from formation. They are orphans of the galaxy, planetary wanderers following long solitary paths through the darkness between stars. Magnetic fields. Influence. Dust alignment. Interstellar dust, composed of tiny grains of carbon and silicates, moves not only under gravity but also under magnetic field influence. These fields thread through the Milky Way like invisible currents, guiding the motion of charged particles and affecting how gas and dust align. In some regions, dust grains spin rapidly, emitting faint microwave radiation. In others, they align with magnetic field lines, polarizing starlight passing through them. Understanding these effects helps astronomers trace magnetic field structure and isolate its influence from other signals. Dust is not passive but responds to magnetic rhythms, forming hidden patterns throughout the galaxy. Heavy elements come from neutron star collisions. When two neutron stars spiral together and collide, they create one of the universe's most violent events, a kilonova. In this brief, blinding explosion, enormous quantities of heavy elements are synthesized: gold, platinum, uranium, and more. These materials are ejected into space, mixing with interstellar gas and eventually forming new stellar generations. Some stars in the Milky Way carry chemical fingerprints of these rare events, enriched in elements that could only originate from neutron star mergers. They are not merely luminous bodies, but record keepers of ancient cataclysms, burning with residue from stellar collisions and cosmic alchemy. The galaxy may have nested bars. At the Milky Way's heart lies a bar of stars, an elongated structure crossing the central bulge. But deep within that bar, astronomers have found hints of another, smaller bar tilted at a different angle, rotating somewhat independently. This inner structure is difficult to observe directly, obscured by dust and distance, but its gravitational influence appears in nearby stellar and gas motion. Nested bars like this may help funnel material toward the supermassive black hole feeding it and shaping core dynamics. The Milky Way's center is not one simple shape, but a layered, shifting complex of light and motion, more intricate than early models suggested. Fresh gas flows in from the cosmic web. The Milky Way is not a closed system but draws fresh gas from the intergalactic medium through long, tenuous streams flowing along the cosmic web. These inflows provide raw material for continued star formation, replenishing what the galaxy loses over time through stellar evolution and winds. Some gas arrives as cold filaments, slipping quietly into the disk. Other streams fall in hotter forms, shock-heated and glowing in ultraviolet or X-ray wavelengths. These invisible rivers sustain the galaxy's growth and evolution, connecting it to the larger universe. Even now, the Milky Way drinks from distant reservoirs, nourished by threads of matter spun across cosmic scales. Hot gas creates chimneys from the disk. When clusters of massive stars explode as supernovae, they create enormous cavities in the interstellar medium. These can merge into superbubbles, vast pockets of hot gas that punch upward through the galactic disk and vent into the halo. The result resembles chimneys, channels where energy, gas, and magnetic fields escape from the disk plane. These structures regulate interstellar medium pressure, redistribute heavy elements throughout the galaxy, and help shape halo structure. The galaxy breathes not merely within the disk, but through towering columns that carry its energy upward and outward into surrounding space. X-rays reveal hidden activity. Though the Milky Way appears serene in visible light, It blazes intensely in X-ray wavelengths. X-rays stream from the galactic core, from collapsed stars, and from matter spiraling toward black holes. White dwarfs and neutron stars in binary systems can accrete matter from companions, heating it to millions of degrees and producing copious X-ray emission. Hot gas in the halo also radiates faint X-rays, revealing the galaxy's larger structure. We cannot perceive this high-energy light with our eyes, but X-ray telescopes paint a dramatically different portrait. Not a tranquil spiral, but a realm of extreme temperatures, compact remnants, and pervasive radiation. Pulsars serve as cosmic clocks. When massive stars collapse into neutron stars, some are left spinning rapidly, with beams of radiation sweeping across space like lighthouse beams. These are pulsars, and some rotate hundreds of times per second with astonishing regularity. They are so consistent that astronomers use them as cosmic timekeepers, tracking their signals to measure distances, test general relativity, and even search for gravitational waves passing through the galaxy. Throughout the Milky Way, pulsars blink quietly, remnants of stellar death, but also beacons of remarkable precision, keeping time not for minutes or hours but for entire epochs, ticking steadily in the silence between stars. Radio astronomy maps hidden structures. Much of the Milky Way remains invisible in optical light, obscured by dust, distance, or faintness, but radio waves penetrate these barriers, revealing otherwise hidden structures. They trace cold, neutral hydrogen gas, outline magnetic field geometries, and highlight emissions from pulsars, supernova remnants, and distant radio galaxies beyond the Milky Way. Using arrays of radio telescopes, astronomers have mapped spiral arms, measured the galactic warp, and discovered star-forming regions cloaked in dust. Where visible light fails, radio wavelengths provide vision. The galaxy speaks in frequencies we cannot hear, but science has learned to translate them into maps of shape and structure. The Sun likely formed in a stellar cluster. Stars rarely form in isolation, but typically in groups, stellar clusters shaped from the same collapsing molecular cloud. Our Sun almost certainly began this way billions of years ago, sharing space with hundreds or thousands of sibling stars born from the same nebula. Over time, gravitational tides, passing stars, and galactic rotation scattered the cluster. Most of the Sun's siblings have wandered far into different orbits, carrying fragments of our shared origin. Some may still shine nearby, indistinguishable among countless stars, lost family in an ocean of light that we have yet to identify definitively. The Sun's siblings are scattered across space. Though the Sun's birth cluster dissolved long ago, astronomers are actively searching for its lost siblings, stars sharing its age, motion, and chemical composition. Using vast surveys like Gaia's astrometric measurements and spectroscopic databases, researchers hope to identify these ancient relatives. A few candidate stars have emerged that may have shared our origin, formed from the same enriched gas cloud. If conclusively identified, they could reveal crucial details about conditions prevailing when the Sun and early solar system formed. Our position in the galaxy is not entirely solitary. Somewhere among the stars, the Sun's ancient kin may still shine, waiting to be recognized. The galactic disk wobbles as it rotates. The Milky Way's disk is not perfectly flat, but wobbles gently, rippling like a spinning plate nudged off balance. This warp is most pronounced in outer regions, where the disk bends upward on one side and downward on the other. It may result from gravitational influence by nearby dwarf galaxies, interactions with dark matter, or internal asymmetries in mass distribution. The wobble rotates slowly, like a vast wave propagating through the stellar population. From Earth we don't perceive it directly, but from external vantage points the Milky Way is not a pristine spiral, but a breathing, undulating sheet of stars, curving gently as it turns through space. Galactic tides distort structures. Just as the Moon's gravity creates tides on Earth, the immense mass of the Milky Way exerts tidal forces on everything within its gravitational influence. Star clusters, satellite galaxies, and globular clusters all experience the galaxy's differential, gravitational pull. Over time, these tides can stretch and distort them, drawing out elongated stellar streams or gradually stripping stars from their orbits. Many of the faint stellar arcs mapped across the sky represent remnants of such encounters, clusters being unravelled, galaxies slowly torn apart. The galaxy doesn't destroy these structures suddenly, but unravels them patiently, strand by strand, over millions or billions of years. The Milky Way's mass remains uncertain. You might expect we would precisely know our own galaxy's mass, but measuring it proves remarkably challenging. Stars and gas constitute only a small fraction of the total. The rest resides in the vast dark matter halo, invisible to all observations. Estimates vary considerably. Some suggest total mass close to 1 trillion solar masses, while others place it significantly higher. The uncertainty stems from difficulties measuring orbital velocities at great distances, a task complicated by limited data and invisible matter's influence. The Milky Way is our home, yet its fundamental properties, including total mass, remain subjects of ongoing research and debate. The Milky Way may outweigh Andromeda. For many years, astronomers assumed that Andromeda, appearing slightly larger and brighter, was also more massive. But recent measurements suggest the Milky Way's dark matter halo may be broader and denser than previously believed. If accurate, our galaxy could outweigh Andromeda despite its more modest visible appearance. This matters not only for comparative studies but for predictions about their eventual merger. When the two galaxies collide billions of years hence, their relative masses will profoundly influence the encounter's dynamics and the resulting galaxy's structure. The Milky Way may appear gentle, but beneath its spiral arms, it may carry more gravitational weight than once imagined. The Magellanic Clouds may be first-time visitors. The large and small Magellanic Clouds, too, prominent satellite galaxies visible from the southern hemisphere, have long been thought to orbit the Milky Way. However, new evidence suggests they may be newcomers, captured only recently in cosmic terms. Their velocity and trajectory through space hint this could be their first close passage. If true, they're not long-standing companions but distant wanderers just now falling under the Milky Way's gravitational influence. Their arrival has disturbed the outer disk and contributed to the galactic warp, as if the Milky Way is responding to a new gravitational presence. The cosmos is full of first encounters. The Magellanic Stream traces their path. Trailing behind the Magellanic Clouds extends a vast ribbon of neutral hydrogen gas called the Magellanic Stream. It stretches over 600,000 light-years, wrapped in curves and arcs across the southern sky. This stream was pulled away by tidal forces as the dwarf galaxies passed close to one another and to the Milky Way, invisible in optical wavelengths. It reveals itself in radio observations, a long trailing signature of motion and loss. The stream may eventually provide material for future star formation in the Milky Way, or settle into the halo, a thread of memory stretching between galaxies, documenting their gravitational interaction. Some gas clouds follow polar orbits. Not everything in the Milky Way follows the orderly plane of the disk. Some gas clouds and even stellar populations move on highly inclined orbits, passing above and below the galaxy's main structure at steep angles. These polar orbits likely originated from past mergers, when dwarf galaxies or stray clouds were captured at unusual angles. Over time, they continued orbiting on tilted paths like comets around a planet. These misaligned orbits are records of disruption, visible reminders that the galaxy is not a closed, orderly system, but an evolving structure shaped by the chaotic flow of cosmic history and gravitational interactions. Giant gas shells mark ancient starbursts. In several regions throughout the Milky Way, astronomers have discovered enormous spherical shells of gas, some spanning hundreds of light years. These shells are remnants of powerful starburst episodes when clusters of massive stars formed together, lived brief lives, and exploded in rapid succession. Their combined stellar winds and supernovae carved vast cavities in the interstellar medium, blowing gas outward in all directions. Over time, expansion slows, but the shells persist as ghostly bubbles marking where the galaxy once blazed with intense stellar birth and death. These are fossils of cosmic fireworks, still echoing across millions of years. Stars occasionally collide in dense regions. Space is vast and stars are small, but in the densest regions of the Milky Way, such as globular cluster cores, stars can pass close enough to interact and even collide. When they do, results can be dramatic. Bursts of radiation, mergers creating more massive stars, or formation of rare blue straggler stars appearing younger than their neighbours. These collisions are rare but not impossible. Over billions of years, the tightest stellar neighbourhoods rearrange themselves through gravity and chance encounters. In these crowded stellar cities, dynamics operate differently, and space is never quite empty. Binary stars can be torn apart. Many stars live in pairs, orbiting each other in gravitational embrace for billions of years. But even these bonds can be severed. If a binary system passes close to the galactic centre's supermassive black hole, or through a dense star cluster, tidal forces can disrupt their orbit, flinging one star away while the other is captured or slowed. In some cases, a companion is ejected from the galaxy entirely, becoming a hypervelocity star speeding through intergalactic space. These stellar breakups occur silently in regions we rarely observe directly, a quiet tearing of ancient partnerships by gravity's indifferent hand. Some stars escape the galaxy completely. Most stars remain gravitationally bound to the Milky Way throughout their lifetimes, but occasionally a star reaches escape velocity, over 500 kilometers per second, and is flung outward, never to return. These hypervelocity stars are rare but real, often ejected by interactions with the supermassive black hole at the galaxy's center, or by supernova explosions in binary systems. Once free, they travel alone into intergalactic space, tiny lighthouses drifting far beyond the spiral's edge. They carry the galaxy's memory outward, becoming solitary pilgrims in the vast darkness between galaxies, isolated but still shining. The Milky Way contains stars from other galaxies. Not all stars within the Milky Way were born here. Some originated in other galaxies, captured during ancient mergers, or flung into our halo from distant regions of the local group. These intergalactic wanderers often move on unusual orbits far from the disk, tracing paths through the outskirts and halo. They can be identified by distinctive composition or motion, stars that don't quite match local patterns. Like cosmic immigrants, they bring stories from other environments, other histories, other skies. The Milky Way is not a sealed system, but a living mosaic, slowly, stitched together by time, gravity, and motion. Gas cycles between disk and halo. Above and below the Milky Way's bright disk, gas rises and falls in a process known as the galactic fountain. Supernovae and stellar winds heat and eject material upward into the halo, where it cools, condenses, and gently rains back down over millions of years. This cycle stirs the interstellar medium, redistributes heavy elements synthesized in stars, and helps regulate star formation rates. It's a quiet respiration, a breathing motion of matter between the dense plane and the vast halo. The galaxy doesn't merely spin, it circulates continuously, exhaling and inhaling, maintaining its structure in motion across vast timescales. Dust grains carry organic compounds. Within clouds of interstellar dust drifting between stars, scientists have detected complex organic molecules, carbon-based compounds forming raw ingredients potentially useful for life. These include polycyclic aromatic hydrocarbons, simple sugars, alcohols, and other prebiotic molecules. Though not alive, they are chemically rich, formed in atmospheres of dying stars or within cold clouds shaped by radiation. These tiny grains, carried across light years by galactic winds, settle into gas clouds that form stars and planets. Some may have fallen onto the early Earth, delivering organic chemistry from space. Galactic dust is not merely debris but cargo of potential, drifting silently through darkness. Molecular clouds may seed solar systems. The birthplaces of stars are also birthplaces of worlds. As planetary systems form from collapsing gas and dust clouds, they inherit chemical fingerprints from their parent nebula. If that cloud contains water, carbon compounds, and other biological building blocks, those ingredients may end up incorporated into comets, asteroids, or planets. Some regions of the Milky Way are especially rich in such prebiotic chemistry. We don't yet know how common life is throughout the galaxy, but conditions for it seem to arise naturally in many locations. The seeds of life may be scattered far and wide, tucked into the galaxy's coldest nurseries, waiting for conducive environments to develop. Some stars rotate, hundreds of times faster than the Sun. Most stars rotate, but some spin incredibly rapidly, completing full rotations in just hours. These rapid rotators are often young, massive, and unstable, with equators bulging from centrifugal force. A few reach such extreme rotation that they fling off material, forming circumstellar disks. The Sun rotates once every 25 to 35 days depending on latitude, but these fast-spinning stars rotate hundreds of times more quickly, approaching physical limits imposed by gravitational binding versus centrifugal force. Their internal structures and evolutionary paths differ dramatically from slower rotators. Their lives may be brief, but while they last, they spin like cosmic dervishes in the darkness. The galaxy is tilted relative to our solar system. From Earth, the Milky Way arcs across the night sky in a graceful band of light, but it doesn't align with our solar system's plane. The galactic plane, where most stars reside, is tilted approximately 60 degrees relative to the ecliptic, the path traced by the Sun and planets across our sky. This tilt explains why the Milky Way rises at an angle and shifts position with seasons. We are part of the galaxy, but our local system is oriented somewhat askew. A small tilted craft drifting through a larger spinning sea of stars, our perspective determined by this angular offset. Some stellar remnants predate the disk. Among faint stars in the halo, astronomers have found white dwarfs, cooling cores of once luminous stars, that are older than the Milky Way's thin disk itself. These ancient remnants formed when the galaxy was young, before its main structure had fully organized. Their existence hints at earlier epochs of star formation, a deeper history written into the outer halo. They have been cooling for billions of years, slowly fading, carrying with them quiet residue from a time when the Milky Way was still gathering shape from primordial clouds. The disk may be bright, but the halo remembers further back. The farthest stars orbit beyond the main structure. The Milky Way's most distant stars orbit far beyond familiar spiral arms, tens or even hundreds of thousands of light years from the galactic center. These stars move through the halo on slow, wide paths, taking billions of years to complete single orbits. Many were likely captured from smaller galaxies during past mergers, now drifting in outermost reaches like distant sentinels. They are faint, sparse, and widely separated, but they help define the galaxy's size, shape, and gravitational extent. The Milky Way is not merely what we see concentrated in the disk. It extends deep into darkness, shaped by wanderers at its edge. The Milky Way's shape is subtly lopsided. Though often pictured as a symmetric spiral, the Milky Way is subtly lopsided in multiple ways. One side of the disk appears thicker. Spiral arms are uneven in brightness and extent. Even the stellar halo is slightly off-center. These asymmetries likely arise from gravitational interactions with the Magellanic Clouds, dark matter substructures, or past mergers. The galaxy is not a perfect pinwheel, but a living structure marked by gravitational tugs and twists, Like a spinning dancer whose form has been altered by the wind. Its beauty lies in this irregularity, a graceful imbalance sculpted by cosmic history. Variable stars help map galactic structure. Certain stars pulse in brightness over regular intervals, expanding and contracting like slow luminous heartbeats. These variable stars, particularly Cepheids and RR Lyrae stars, have well-known relationships between brightness and pulsation period. By measuring how long a star takes to brighten and dim, astronomers can determine its true luminosity, and by comparing that to apparent brightness, calculate its distance. These stars serve as cosmic measuring sticks, helping map the Milky Way's shape, structure, and scale. They are lights that measure darkness, blinking beacons scattered throughout the spiral, each one a calibrated marker in three-dimensional space. The Gaia mission revolutionizes galactic astronomy. Launched by the European Space Agency, the Gaia spacecraft is creating the most precise map of the Milky Way ever achieved. By measuring positions, motions, and brightness of over 2 billion stars, Gaia reveals the galaxy's three-dimensional structure and motion through time, with unprecedented clarity. It has uncovered stellar streams from shredded galaxies, mapped the disk warp in detail, and traced the Sun's orbit with exquisite precision. With each new data release, Gaia deepens understanding, transforming a hazy smear of stars into a sharp living map. It represents astronomy's most ambitious stellar census, a quiet revolution unfolding among the stars. The galactic plane marks the densest stellar concentration. If you observe the night sky from a dark location away from cities and lights, you may see a hazy river of starlight crossing overhead. That's the galactic plane, the thickest slice of the Milky Way's disk. It's not a line, but a depth, a vast flattened band where the majority of the galaxy's stars concentrate. Through this plane, stellar density is highest, dust layers are thickest, and star formation is most active. From our vantage point, we gaze along the disk's length, peering through its richest corridors. This band isn't merely beautiful, it's the crowded, humming heart where most stars live, evolve, and die. The night sky brightens toward Sagittarius. The core of the Milky Way lies in the direction of the constellation Sagittarius, a dense, glowing concentration of stars, gas, and unseen mass. From Earth, we cannot see the very center in visible light. Dust clouds completely obscure our view, but the region glows with concentrated brightness in infrared and radio wavelengths. Even with unaided eyes, the area appears more crowded and luminous, filled with overlapping light from billions of stars. We orbit far from this center in a quiet suburb of the galactic disk, but when we look towards Sagittarius, we glimpse the crowded metropolis at the galaxy's heart, the ancient core around which everything revolves. We see the Milky Way edge on from Earth. Because we live within it, we cannot look down upon the Milky Way from above like viewing a map. Instead, we see it from inside, a flat ribbon of stars stretching across the sky, curved only by the horizon and perspective. This edge-on view compresses the galaxy into a single arc, making it extraordinarily difficult to grasp its full three-dimensional structure from our embedded perspective. It required centuries of observation, cataloguing, and mathematical deduction to realize the spiral nature of our home. From Earth, we gaze through the galactic disk like standing in a forest and looking along rows of trees. We cannot see the shape we're part of, only the vastness surrounding us. The galaxy holds more than we can ever see. Even with our most sensitive instruments spanning all wavelengths, we glimpse only a fraction of what the Milky Way contains. Light is blocked by dust barriers. Motion is hidden in silence. Dark matter outnumbers luminous. Stars by factors of 10 or more. Between every star lies emptiness, and within every empty space resides potential. The Milky Way is not just what we observe, but what we suspect, infer, and long to understand. It holds ancient light, future stars, drifting worlds, and questions still without answers. Within that vastness, somehow we find ourselves, one planet among many, orbiting a quiet star, floating through a story too immense for any eye to encompass fully. Closing. And now the stars begin to dim behind your thoughts. We've drifted through countless quiet truths together tonight, from the warped shape of the galactic disk to the most distant halo stars, from newborn suns to ancient remnants, from dust and gas to light and shadow and everything between. You've wandered through stellar nurseries, danced along spiral density waves, and gazed toward the galactic heart glowing behind veils of dust. You are part of this galaxy, not merely a passenger on Earth, but a participant in its long and luminous unfolding. The iron in your blood was forged in stellar cores. The oxygen you breathe was created in ancient explosions. The atoms composing your body trace their lineage to the earliest cosmic epochs, born from the same matter that now fuels suns and whispers through clouds of interstellar dust. Tonight, as you rest, the galaxy continues its ancient rotation. Stars are forming in cold molecular clouds. Light is travelling across vast distances. Silent orbits continue their patient progression, and you are floating within it all, a small warmth in the darkness, resting in the spiral arm of a quiet, radiant sea of stars. If you happen to still be awake, feel free to explore more about the universe in the next video. I hope you sleep well and dream softly among the stars. Good night from late space.